Anyone else? Last call? Okay. Yeah, I don't need the test. Here. You can keep that. All right, so the correct answer should have been what? 90,000. All right. Okay, so today we are going to start a new section, 11.5. And this is called Implicit Differentiation. So, do y'all remember what we did last class? We did derivatives of logs and exponential functions, right? Okay, today we're going to introduce a new type of differentiation that is going to allow us to take derivatives of some things that we cannot take derivatives of right now. So let me start this out with an example, all right? Just to get the idea motivated here. As an example, what I'm going to do is put up here an equation, x squared plus y squared equals, let's go 9. Now I don't expect that everyone knows what that looks like, but there is a graph that goes with this equation. Does anybody know what that is a graph of?
Is it a circle?
That is a circle. So let me show you how I could maybe convince you it's a circle. If I give you some values of x, then maybe we can come up with the y values. So like for example, if I plug in 0 for x, then that means y squared has to be 9. Do y'all see that? And what number squared is 9? 3 or negative 3. Do y'all agree with that? So if x is 0, y could be 3, or it could be negative 3. Make sense? Let's do it the other way around. What if y was 0? What if this y was 0? Then what would x be? 3 or negative 3 again. Do y'all see that? So I get 3 or negative 3. So if I start to try and draw the graph of this, that means plotting the points. The point 0, 3 is straight up 3 units. The point 0, negative 3, y'all understand I'm doing these as like ordered pairs. This is the x, the y, the x, the y, yes? Okay, so this next point would be down here, right? And then this point 3, 0 would be to the right 3. And then the one to the left, or this one would be to the left 3. So far, this kind of looks like this is going to be a circle maybe, right? So maybe we try something else. How about 1 for x? If 1 is x, let me actually plug it in here. What's 1 squared? 1. So we get 1 plus y squared equals 9. If I subtract 1 on both sides, I get y squared is 8. And then I take the square root on both sides, and I get y is equal to plus or minus the square root of 8. And then we could get our calculator out. What's the square root of 8? 2.8 something? Okay, so that means I get 2.8 approximately, and then I could also get negative 2.8. Make sense? You plug in 1 for x, you're going to get 2 answers. So if I plug in 1 for x, I go up 2.8, I go down 2.8. And then I could plug in 2 and do something similar, right? And if I plug in 2, I'm going to get something like this and then like that. And if you put all these together, and this is a terrible picture, but if you get all the answers, all the different possible points that satisfy this equation, you get a circle. All right? So that is the equation of a circle. The problem that we run into with the equation of a circle is this. It is not a function. So do you all remember in, what's that class before this, 1324? Do you all remember this thing called the vertical line test? That's a test that you do to see whether or not the graph you're looking at is a function or not. This circle fails to be a function because if I draw a vertical line, I hit it twice, and I'm only allowed to ever hit it one time for it to be called a function. So this right here is not a function of x. It is not a function of x, okay? However, if I actually just go to a point, let me just pick some random point here. How about I pick this point right here? How about I pick this point right here? Would you agree that there is a tangent line that has a slope on that at that point? In other words, there's some line that would run tangent to that curve, right? And it has some slope, and I actually don't know what it is, but we should be able to find it. Like, it does exist, right? And I can do that for any point on the circle. Agreed? And to get the slope of the tangent line, we need to take a derivative, don't we? But this is not like anything we've seen before. Everything that we have had before, if you look back in all of our notes, everything we've ever had was y equals something, right? Or we wrote f of x equals something, and then we took the derivatives, didn't we? We never had an equation like this. Agreed? So maybe all we need to do is solve this for y. Yeah? If we solve it for y, wouldn't it look like this? Let's try that. Let's just see, and it's not gonna work. All right? Let me show you why. So if I just try and solve this for y, then I could subtract x squared on both sides. So I take x squared away over here, I take x squared away, and I get this, right? The next step to get y by itself would be to take the square root on both sides. And when I do that, I'm going to run into the problem. And the problem is that when you do a square root, you get a plus or minus. And so the left side becomes y, and the right side becomes plus or minus, like this. Go with me? The reason this is a problem is because this is not one function, this is actually two, right? There's a positive one and there's a negative. There's two different functions. And so we never did that before. I never said y is equal to two different things, a positive and a negative, right? So finding the slope of this red line, right? Finding the slope of that line is not going to be as easy as solving for y and then just doing a derivative. So what we need is an entirely new kind of approach, and that's where this idea of implicit differentiation comes from. All right? It's going to allow us to take derivatives of graphs that do not pass the vertical line test. All right, let me say that again. Implicit differentiation is going to allow us to take the derivative of graphs that do not pass the vertical line test. All right? Now, I'll try and motivate this even more, just with a kind of more of a real-world physical example. Like, let's say that I have some object. Let's say it's I don't know, a dog. That's the first thing I thought of. And here's a dog, okay? And we're looking at this dog from the top, all right? This dog starts running around in the yard, okay? This dog's going to run around. So if this dog starts running, right? Well, you know what? Let me make the dog run like this. The dog starts running, then if I were to look at the slope of the tangent line, that slope of the tangent line would almost give me like a direction that the dog was running at a specific point, right? So like right at that instant, the dog was running in that direction. Agreed? Okay, so the dog starts running around. And I know this dog analogy is kind of stupid because you never really need to know this, but just what I'm trying to get at is this. Everything we've done up to this point, we can handle it so long as it passes the vertical line test, right? So if this dog continues to run, I can do derivatives so long as the dog runs a certain way, right? And it doesn't ever turn back on itself. So like if the dog starts doing this, oh, I've run into an issue because this graph is no longer a function. Do y'all see that? But this dog still has directions at all these points. And there's nothing that tells the dog that they have to follow some given path. They can do anything they want, right? And so I need to be able to find slopes of tangent lines for things that are not functions. Got it? Implicit differentiation is what we're going to use. Okay. So now, before I can do it, I need to remind you of something. If you don't like the dog analogy, then make that like a rocket that's being fired. You know, you launch a rocket and you're wanting to see what it's, right? The rocket's going to kind of behave however it wants to behave. All right, so before we do it, please let me remind you of something that we already learned that you must understand completely to do this. Recall the chain rule. So as an example, let's say that you had y equals 2x plus 1 to the 5th power, and you were asked to find y prime. I'm trusting that everyone here would be able to do this. And we've done this already, right? So you have to look at this as something being raised to a power, right? So you'll bring that power out. 5. And then what will I write? The inside, 2x plus 1. Then to the 4th power. All right? So far, that's our answer. What is the next very important critical step? Derivative of the inside. The derivative of the inside is 2. Just 2, right? That okay? That's the key. That 2 right there is the part that really you got to make sure you understand. So this really becomes 10 times 2x plus 1 to the 4th. All right. Next example. And this example, you're going to look at it and think it's actually easier than what we just did. How about the derivative of x to the 5th? What's the derivative of this? It's not a trick question. 5x to the 4th, right? That's what we've said. I mean, that's what we would all agree upon. What I'd like for you to do, though, this time, is I want you to think about it like a chain rule. Okay, I want you to think about it like you're taking derivative of this. All right, so the first step would be that you bring the 5 down, don't you? You bring the 5 down. And then you take the base here, the x, and you raise it to what power? 4, right? The next step of the chain rule is to then take the derivative of what's here, right? And what is the derivative of x? 1, isn't it? It's 1. So I'm going to write here times 1. And I'm going to point out to you that that is because the derivative, I'm going to use some different notation with respect to x of x. This was a different notation that we had looked at briefly. But this just says, hey, I'm taking the derivative, I'm treating x like my variable, and I'm taking the derivative of x. And the derivative of x is 1. Yes? Now, 1 times 5 is 5, so this just becomes 5x to the 4th. So that's a lot of thinking, right, to get to the answer you already knew right when I started this, right? But we need to be able to think about it this way to be able to do implicit differentiation. Are we good? Sure? Okay. That's all you need. Here we go. Let's go back to that circle and let's try and figure out the slope of the tangent line. So here's the example now. X squared plus y squared equals 9. I want us to find y prime. In other words, I want us to be able to find the slope of the tangent line. So the way we do this is we use what we call implicit differentiation. All right. And to do that, what we're going to do is we're going to take the derivative on both sides of the equation at the same time. All right? So just watch me write it down first. I'm going to take the derivative. I'm going to treat x as my variable. And I'm going to take derivative of the left side. And then equals, then I'm going to take the derivative, treating x like my variable, of the right side. So please note that this right here and this right here is just stating we are taking the derivative of both sides. All right, so that's just me saying, hey, look, I'm about to take derivative of both sides. Here we go. You ready? Let's start with the right side, because the right side is the easier one. What is the derivative of 9? 0. Because the derivative of a constant is 0. That's always the case. So do you agree that I can write equals 9? Yes? We good? Okay. Now, on the left side, I have two things being added together, don't I? When we have addition, we can do them separately, can't we? All right. Here's where we have to think. What is the derivative of x squared? 2x, right? 2x. Now, what if we looked at it like this? If this was x squared instead, let's see what we would get. We would get 2 comes out, that's a 1, and then what's the derivative of what's in here? 1, right? And so you get 2x. Yes, there's nothing new here. It's 2x, all right? I'm not trying to trick you. That's 2x. So derivative of this is 2x. Great, wonderful. Plus, now this is the part that is the tricky part, all right? This part right here. What is the derivative of y squared? So what I want you to do is on the side, just let's think about this. If I have y squared, and I'm trying to take its derivative, right? That's the sign for derivative. Then you're going to bring the 2 out, right? Just like the chain rule. You're going to bring the 2 out. And then you're going to have y to what power? First power, right? Then the chain rule says now take the derivative of what's down here. And what is the derivative of y? It's the derivative of y, isn't it? I mean, the derivative of y is the derivative of y, which is exactly what I'm trying to find, isn't it? So what I'm going to put out here is y prime. Now don't confuse, that's a 1, that's a y prime. Do you see that this is not a 1 right now? It's not a 1 because what was the derivative of x? The derivative of x is 1, right? But the derivative of y is not 1. The derivative of y is the derivative of y. Huh? Y'all see the difference between these? You sure? So our answer is 2y, y prime. 2y, y prime. That still looks like a 1. Y prime, like that. Questions? Sure? You could write y prime as dy dx, which if you've seen this before, that's the way they write it. Okay, I'm going to do that. I'm just not ready to do it yet. Okay, y'all all right with that? Okay, so we don't have the answer yet. Remember, we're trying to solve for y prime, right? We want to know what y prime is. And take a look at this. What we've done, there's a y prime in it now, right? So what I'm going to do is take that equation, and I'm going to solve it for y prime. So 2x plus 2y, y prime equals 0. I'm going to try right now to isolate this by itself. So what I'll do is I'll move the 2x to the other side, which makes it negative 2x. And then what? Trying to isolate that. Divide by 2y. Negative 2x over 2y. So y prime equals negative x over y. So I can cancel these 2's. That's your answer. Now, this derivative is different than any derivative that we've done up to this point. Every derivative that we've ever done in this class so far, our answer has only had x's in it. Like the derivative of something only had x's in the answer. This problem, when we did it, the derivative actually has x and y in the answer. Let me explain why it is this way. Let's go back to the picture. Okay. Let's go out to this value 1 right here. Okay? Do you remember when we plugged in 1, we got 2.8 and negative 2. Was it 2.8? It was 2.8, negative 2.8, right? So when we plugged in 1, we were here and we were here. Now, what if I wanted to know the slope of the tangent line here? What if I wanted to know the slope of the tangent line? I'm supposed to use this formula, right? Which says the slope of the tangent line is negative x divided by y. So what you're going to do is you're going to take your x coordinate, multiply it by negative 1, and then divide it by the y coordinate of that point. Right? So you need both the x and the y coordinate to get the answer. Do you see why we would need the x and y? Look at this one right here. Don't these have the same x coordinates? So by giving you just the x coordinate, you shouldn't be able to give me the derivative. You should have to give me both the x and the y so I can distinguish between this point and this point. That make sense? So we should get different answers for those two, right? Okay, so let's try it. What is the slope of the tangent line here? Well, what's the point? What was that point again? It was 1, 2.8. That was our x, that was our y. So what is the slope of the tangent line there? This. It's negative what? Negative 1 over 2.8. And someone do that on the calculator. It's approximately 0.3 something. Negative 0.35? Negative 0.35. So do we agree at this point right here that it looks like we have just a slight little negative slope? And our answer confirms that, doesn't it? Now, what would the slope of the tangent line here be? Well, our point's different, isn't it? It's 1, but it's now negative 2.8. So if we find the slope, it's going to be negative 1 over negative 2.8. So the answer is approximately positive 0.35. So we're getting the same slope, except it's positive instead of negative. And that's because the y coordinate changed. The x coordinate didn't change, right? The y did. So with these equations, when we can't solve for y and we have to take the derivative implicitly, our answer is normally going to have both the x and the y coordinates in the answer. Okay? Questions? Just out of curiosity, what about at the very bottom there? What's that point? What is that point that's on our graph right here? It's the point 0, negative 3. Without using the formula, what should the slope of the tangent line be there? What should the slope of this line be? 0, right? Is it? According to our formula? We're supposed to go negative x. What's x? 0 over 3. So you get 0. So the formula works for that. Also works for this one. That's the point 0, 3, and it doesn't matter when I plug in negative x. Negative 0 is still 0. You get 0 over 3. What about here? That tangent line is a vertical line, isn't it? It's undefined. Now let's see what happens here. This is the point negative 3, 0. So if I try and plug in negative 3, 0 into this, the y is 0. I'm going to get division by 0. And division by 0 is not allowed, which means that this is undefined. And do you all remember that when you talk about slopes of lines, vertical lines have undefined slopes. Their slopes are undefined. So the formula is perfect. Like, it matches exactly what's happening in this picture. All right, let's try a different equation, and let's go through the same process and just see how this derivative thing can get a little bit messy. Okay, here we go. How about, all right, let's do this one. Y squared minus y minus 4x equals 0. Find slope of tangent line at the point 0, 1. So this point 0, 1 lives on this graph. Now I'm not drawing this graph for us, all right? The first example I did was a circle, and that was just because circles are easy to look at, and this one looks like something else. We don't know yet, or we're not even going to look at it. But we want to know what the slope of tangent line is at 0, 1. So we need to find y prime first, right? So we're going to find y prime. So I'm going to take the derivative on the left side, and I'm going to take the derivative on the right side. I'm using implicit differentiation. Now carefully analyze what's happening over here. We have three separate things, right? Three things separated by addition or subtraction, so I can do them individually. What is the derivative of y squared? 2y prime. 2y prime. That's the exact thing we did just a second ago, right? The 2 comes out, y to the first power, then the derivative of the y, which was y prime. So this is 2y times y prime. Okay, then I have minus. What is the derivative of y? Just y prime. Just y prime. Now, look at it this way. If you tried to look at that, y is y to the first power, then if you take the derivative of this, the 1 comes out, right? Then you'd have y to what power? 0, and then times the derivative of what's down here, which would be y prime. If you're trying to do chain rule, this is what would happen. Y to the 0 is 1. So this is 1 times y prime. Yes? Okay, so this is just y prime. And then minus, now what's the derivative of 4x? That you can go back to your normal, like what we've learned in the past, everything still works the same. So derivative of 4x is 4. And we're done on the left side, right? Equals 0. That is the differentiation step. I've taken the derivative, right? Next thing is to solve for y prime. And this one is a little different because do you see that these both have, this has y prime in it and this has y prime in it? See that they both do? So here's what the next step is going to be. And this is the step you'll use whenever this happens. Whenever you see more than one y prime, what you will do is move all your y primes to one side and everything that does not have y prime to the other side. Okay? So this has y prime, this has y prime, this doesn't. So I'm going to move the negative 4 to the other side. It'll become positive 4. Did you all catch what I'm saying there? Whenever you have y primes, multiple y primes, you isolate all the y primes on one side, anything that doesn't on the other. Why do you think I did that? What can I do on the left-hand side right now? Not cancel them. You can do something with them, though. They both have y prime. Both terms have y prime, right? In common, right? They have a common factor of y prime. So you can do like a GCF, and you can pull y prime out of the left side. And what you'd be left with is 2y minus 1 equals 4. See what I did? Just pulled that y prime and y prime, pulled it out, and then that left me with the 2y, and when I pulled the y prime away from here, I still have a 1 there. If I distribute the y prime back through, I get this, right? Now, I'm almost there. I'm trying to get this by itself. Here it was appearing in two places. Here it was in two places. But now, because of this GCF, I've almost got it by itself. I need to get rid of this that's being multiplied. So how can I get rid of that thing that's being multiplied on both sides? Divide it, right? Divide it on both sides. So y prime will equal, we divide this side, I'll just throw it in here. I divide this side by 2y minus 1, and then I divide this side by 2y minus 1. These cancel, and I'm left with 4 over 2y minus 1. That's my answer. That's just the derivative, right? That's just the derivative. What do I still need to do? Find the slope of the tangent line at x is 0 and y is 1. So we're going to plug in whatever we need into this. Look at this formula. It only has a y in it, doesn't it? That's okay. This particular graph, you only need to know the y coordinate to get the derivative. So my slope is going to be equal to 4 over 2 times what? 1 minus 1, which is 4 over 1, which is just 4. I think I'm off camera here. Yeah, I'm off camera. So this is just 4. So the slope is 4. Is that all right? Let's do one more, and then we're going to do a little bit of a different notation, and then we're going to try and do a word problem. So same instructions. I want us to find the slope of the tangent line of 2x cubed y minus x cubed plus 5 equals 0 at the point -1, 3. Okay, this is definitely harder than the ones we just did. Can anybody see why this is harder? Because you have 3 different terms here, right? But this term right here has multiplication between your variables. Do you see that? And when you try and take the derivative of multiplication, you must use the product rule. And that's going to be a little bit problematic, all right? But let's go ahead and start with just writing down we want the derivative with respect to x of 2x cubed y minus x cubed plus 5 equals the derivative with respect to x of 0. That's just letting everyone know we're about to take the derivative implicitly, which means we're going to do it on both sides of the equation. Let's take care of the easier parts first. What's the derivative of 0? 0. Okay. What's the derivative of 5? 0. What's the derivative of x cubed? 3x squared. And there should be a minus in front of that, right? So do you agree with that part? This is the easy part. Derivative of x cubed is 3x squared, derivative of 5 is 0, derivative of 0 is 0. The only thing we need to figure out is the derivative of this, right? I'm going to do that on the side because I really want to make sure you understand what's about to happen. Okay, there's my product, right? I'm about to take derivative of this. The product rule says I take the derivative of this, I multiply times this, then plus the derivative of this times this, right? That's the general formula. Derivative of this times this plus derivative of this times this. So what is the derivative of 2x cubed? So I'm about to take derivative of this. Derivative of that is, what did you say? 6x squared, then what? Times y. So that's the derivative of the first one times the second one. Yes? Plus, what is the derivative of this? Y prime, right? The derivative of y is y prime. Y prime times what? 2x cubed. So the derivative of 2x cubed y is actually 6x squared y plus y prime times 2x cubed. Product rule within there, right? And you have to recognize the derivative of y is y prime. Is this clear? Okay, that's just this first part right here. So I'm going to just slap that over here. 6x squared y, and then plus, I'm going to rearrange that, 2x cubed y prime. I just kind of rearranged this. I put the 2 out in front, I put the x cubed out in front, just slap the y prime on the back. All right, there's our derivative. What now? Isolate it. Let's get this guy by itself. So let's take everything that does not have y prime, move it to the other side. So I will still have 2x cubed y prime here. Now, when I move this one to the other side, it becomes a positive. When I move this one to the other side, it becomes a negative. So we have 3x squared minus 6x squared y. Questions on that? Final step, what? You're trying to get this by itself. So do what? Divide everything by 2x cubed on both sides of the equation. So y prime will be equal to 3x squared minus 6x squared y over 2x cubed. That's our derivative. Divide this side by 2x cubed, divide this side by 2x cubed, done. We have y prime by itself. We good? Okay, now we haven't answered the question, have we? Question is, what is the slope of the tangent line at this point? So the slope of the tangent line will be equal to this thing right here, replacing all of the x's with what? Replace all the x's with -1, replace all the y's with 3. So let's see, this will be 3 times -1 squared minus 6 times -1 squared times 3 all over 2 times -1 cubed. So just make sure you do your order of operations correctly here. Let's do all the exponents first. So what's -1 squared? 1, -1 squared, 1, -1 cubed, -1. So we have 3 times 1 minus 6 times 1 times 3 over 2 times -1. I know that looks messy, but... And now do all the multiplications before you do any subtractions. So this is going to be 3, what? Minus 18 over -2. And 3 take away 18 is -15 over -2. And a negative over negative is positive, so you get 15 halves. As a decimal, it's 7.5, but we can leave it as a fraction. So if we were to graph this curve, and if we were to draw it, and we were to go to this point, -1, 3, can you turn on the projector, top left? If we were to draw that graph and then go to the point -1, 3, we should see a line there. Should that line be sloped up or down? Up? Up a lot or not a lot? What is the slope of that line? 7.5? Is 7 a steep slope? That's pretty steep. Because if you have a line, a diagonal line has a slope of what? Diagonal like 45 degrees? What's the slope of that? 1. That's 1. So slope of 7 is going to be very steep. Relatively steep. I may not be showing you this. Can you, don't press off, but you see on the top row it says like HDMI, then do VGA, and then you're going to switch back to HDMI after that. Go ahead and switch it back. This computer has just had all sorts of issues. Nothing, huh? Try one more thing. Well, doesn't look like it's happening today. That's weird. All right, you can shut that off, top left or somewhere up there. Guess you'll just have to take it on faith that we did all the math correctly, okay? All right, now, what we're going to do next is we're going to go through the same 3 problems that we just did, but I'm going to use a different notation. And that's just setting us up for the next section, because we're going to use a different notation in the next section.
Y prime, we can write it as dy over dx, right?
That's what I'm about to show you, yes. So remember, recall that when it comes to notation, y prime is the same as writing dy dx. That's the notation, that those notations are interchangeable. So if I go back and I take a look at that equation, the first one we did, x squared plus y squared is 9. And then I took the derivative on both sides. We said that the derivative of x squared was what? 2x. And then we said that the derivative of y squared was not 2y, it was actually 2y y prime. We could write that 2y, but instead of y prime we write dy dx. Right? That's the same notation. Equals what? 0. And then what you would do is you would try and isolate that little thing by itself. So you would move the 2x over and then divide by 2y. So you get the same exact answer at the end. You'd get dy dx equals negative x over y. Is that all right? Do I need to go through the other 2 examples? You're all right? Okay. All right. So I want to try and get you thinking about the next problem. So I'm going to start talking about the next section because I want us to at least have seen it, and it's a hard section, so expose you to it a little bit. That's it for the 11.5. Just that's implicit differentiation. Now 11.6. Related rates. Related rates is hard? Yeah, this is most of the time students say this is difficult. Okay, I'm going to try and do this with an example. I'm going to have to go off camera for it, and I'm sure you don't mind that. What I'm going to do is I'm going to take this ruler and I am going to see if I can do this without messing anything up here. I'm going to lean this ruler up against the wall there and try it like that, okay? Everyone see that? And then what I'm going to do is I'm going to grab the bottom of this ruler and I'm start pulling it away from the wall. And I'm going to try and pull it at a constant speed. Just pull the bottom. So what's going to happen to the tip of the ladder up there, or the tip of the ruler? It's going to start falling, right? Now, let's just do it one time. Okay? Okay, you see that happen? All right, I'm going to do it again now. I want you to pay attention to how fast this point is moving. As I pull away, I'm going to pull at a constant rate. But I want you to see, does this point start to, as it comes down the wall, is it slowing down, speeding up, or staying the same speed the whole time? Let's see. Does it look like it's speeding up to you? You can do it one more time. Seems like towards the end, it really had to make up a lot of distance in a short period of time, didn't it? I think right around, like about at this point right here, it really has to, as I move it a little bit, it's going to have to travel quite a distance. So, okay. You get the idea there? This is a classic problem to introduce you to related rates. And think about that as being a ladder. So there's some poor guy up there, and the ladder slips out from underneath him, right? And he's going to come down the wall. All right? So you've got this wall, and you've got the ground, and then you've got this ladder. I don't know if I can show you. I doubt you can see it. Yeah, you can probably see that. Can y'all see that? A little bit? I got a scar here. I fell off a 24-foot ladder. Yeah, I was very lucky, actually, very lucky. I mean, if you know anything about falling, you can fall from 5 feet and be paralyzed for the rest of your life. I fell off a 24-foot ladder. I was like at the top. I was like, my feet were on the second to last rung. My shins were up against the last thing, and I was leaning up against a house changing a light bulb. And I had everything tied. I had the base of it tied to the anchor and stuff, but it just, something happened and it just came out kind of sideways. And it was, man, that was a long fall. I mean, my whole life seemed to flash. And fortunately for me, I'll try and draw a picture. This is actually what it looked like. This was the wall, and my ladder was like this. The wall wasn't that tall, but yeah, I can relate to this problem. So that poor guy is me. So it fell, but this was grass. It was ground, right? It wasn't concrete, and there was a slope to it. So when I came down, I hit and like went backwards and put this arm down, and just blew this arm up. But I was lucky not to blow my shoulder up or my back or anything like that. So yeah. It was not even my light bulb. It was my neighbor's light bulb. He was a retired military guy, and I was just doing him a favor. He felt terrible about it. Okay, we've got this ladder. Let's say it's a just out of for memory's sake for me. Let's make it a 24-foot ladder. Okay, so that's a 24-foot ladder, and let's say it begins to slide out on the bottom. And let's say that it starts sliding out at a rate of 3 feet per second. 3 feet per second. So every second, the bottom starts moving out 3 feet. Now we will tie this, we will do related rate problems that are more tied to business, but we want to start out with a very concrete physical problem that we can all kind of see before we start doing anything else, all right? All right, 24-foot ladder, the bottom is moving out at 3 feet per second. Let me just present the problem to you first, and then we're going to talk a lot more about what's going on here. How fast is the tip of ladder, tip or the top, whatever you want to call that. I'm talking about this point. Moving down the wall at exactly the moment it is 5 feet off the ground. That's the question. And this is a very unusual question. You probably have never seen a question like this ever presented to you. How fast is the tip of the ladder moving down the wall at exactly the moment it is 5 feet off the ground? So remember when I was pulling this thing off the wall? You said that the tip of that thing was coming down, but it was speeding up. So what I'm asking for is the speed of this point at exactly the moment that it's 5 feet off the ground. Yes? Let me draw a picture. This is going to be a picture at the exact moment that I'm talking about. So we've got the ladder. This is 24 feet. And this side right here is 5 feet. Do you agree? That side right there is 5 feet. This is a picture of the exact moment that I'm referring to in the question. Do you agree? The exact moment in question is from this picture. 24 feet, that's 5 feet. So how fast is that point moving at exactly that moment? That's a very weird question, isn't it? Very weird question. Does it even seem possible that we can answer that question? I mean, it's got to be, right? Or else we wouldn't be doing this? Okay. But the question is, how are we going to do that? So let me illustrate something to you, right? How fast am I running right now? 0? Like I'm not running, right? Okay, so what I want you now think about is if I come running now, right there. See when I snap my fingers, how fast was I running? I did have a speed, didn't I? Okay, so I'm running, and imagine you've got a camera, and at some instant you take a picture, right? At that instant, I was moving, and I had a speed at that instant, right? That's what we're trying to do, is we're trying to like watch this ladder come down the wall, and then take a picture. Here's the picture, and at that exact moment, how fast was that moving? Understand? Now, if you go a little bit further in time, when this ladder is now 3 feet off the ground, it's going to be a different speed because it's speeding up, right? So we are trying to take snapshots in time and find speeds, how fast things are changing. With me? Kind of? Yeah. The thing is, you have to remember that this ladder is in motion. Because if I'm just standing here and asking you how fast I'm moving, I'm not, right? You have to remember that even though we've snapped the picture, this thing is in motion. How in the hell are we going to figure this out? Okay. Well, this is our exact moment picture, right? I'm going to draw another picture now. This picture is going to be the ladder again. 24 feet. That doesn't change, right? The ladder is always 24 feet. But this time, everything's in motion. This point's moving that way, that point's moving that way. This is our general picture. I'm going to call it general picture. This is how I do most related rate problems. I draw a general picture where everything's in motion, and I draw an exact moment snapshot picture. So I've got two pictures, and I've got the question that's being presented. With me? What we're going to do now is we're going to try and identify two things. We're going to try and find what we're given in the problem, what information are we given, and what is it that we want. Okay, this is where things get weird, all right? You all ready? If it's not weird already for you, now it's going to get even weirder. I am given, I forgot to put the 3 feet per second, didn't I? 3 feet per second is how fast that's moving. So the first thing I'm going to look at is what am I given in the problem? I'm given how fast the ladder's moving, right? And I'm also given how long the ladder is. The rate at which the ladder moves, 3 feet per second, is a vital piece of information in the problem, right? 3 feet per second. I'm going to write that down. 3 feet per second. 3 feet per second is a speed, isn't it? It's a speed. It's a rate of change. It's how fast something is changing, yes? It's the change in this distance right here over time. So if you measured from here to here, whatever that distance is changing at 3 feet per second. Agreed? So since this distance from here to here is changing, it's a variable. And so I'm going to call that distance x. Okay, I'm talking about the distance from here to here. I'm going to call that x. Now I'm going to write something down up here, and let's just see if you can wrap your head around this. This 3 feet per second is equal to dx dt. Now let's understand what I just put up there. When you see the d here, it means derivative, all right? That's what it stands for. That's what it's represented this whole time. This is the rate of change in x with respect to t. T here is time. This is telling me 3 feet per second is telling me how fast x is changing with respect to time. You follow me or not? Yes, you sure? So I am given the rate at which x changes with respect to time. That is given information to me, right? What is it that I want to know in the problem? The speed of this point coming down, right? Now this point coming down, I could measure the distance between here and here, and that distance is changing, isn't it? So it's a variable. I should call it something, but not x, because I'm already using x. So why don't we call the distance from here to here y? Okay, y is fine, right? So in my general picture, x changes and y changes. In my snapshot, this is stuck, isn't it? So what I want in the problem, what is it that I want? How fast is the tip of the ladder moving down the wall? When we say how fast, we need to be thinking speed. When we're thinking speed, we need to be thinking derivative, right? This was a speed, that's a derivative. So we're actually asking for a derivative as an answer. It's the change in what over what. We're given the change in x over time, right? What we want to know is the change in y over time. Right? How fast is y changing with respect to time is what we want to know. And since I want to know that, I'm going to put question mark. So I want dy dx. I'm given how fast that's moving. I want to know how fast this is moving. When do I want this? At exactly what moment do I want this? At this, okay, at 5 feet, but when what is 5 feet? When x is 5 feet? When y is 5 feet, right? When that y is 5 feet is when I want to know how fast it's moving. So I want this at exactly the moment y is equal to 5. Look, I know this is the first problem. This is going to look weird, and let's just try and plow through this, then we'll do another one, and we'll spend next week doing them. All right, so we took the word problem, we drew a picture of the general situation, a snapshot, we assigned some variables, and then we defined what it is that we were given and what it is that we want in exactly the moment we want it. Yes? Okay. So where does the implicit differentiation come in? Where does differentiation come in at all? Well, the next part of the problem, the next thing you need to do is you need to find an equation connecting your variables. Okay, that's the next part. So when I say connecting the variables, I mean this variable here, x,